Welcome to our fax devices courses. We shall continue today with the fax Var Compensator. We are discussing that will be a continuation of the previous discussions. Now, first of all, we will discuss about the MSC TCR SVC. MSC stands for actually mechanically switched capacitor, and TCS is thyristor control reactor, and that combinations will give you the shunt compensations. Please understand it. Actually, this is a grid connections, and we require a step down transformer to match the rating of this TCR mostly. So, we have a TCR, and apart from that we have a mechanically switched constant capacitor, and we will have a small value of the inductor, so that it will actually prevent the inrush current through the capacitor. And there is a harmonic, because TCR will generate some amount of the harmonic that will be suppressed by this actually harmonic filter. So, this kind of combination is called MSC TCR SVC. Here, instead of the fixed capacitor, mechanically switched capacitor are being placed. There is advantage of it, because you can connect and disconnect instead of connecting permanently with the voltage stress, and it is normally used where we require a less amount of switching, because you know that there is a constant var, let us say around 14 MVA. So, you keep it is around 14 MVA. If at a moment it is 13.6, then it will have a capacity, one TCR will have a capacity to actually inject 1 megavar negative. So, actually it will inject actually minus 0.4 MVA. So, this is the concept of this MSC TCR. So, you will not be switching very frequently this capacitor only for the maintenance or any isolation issues. It is same like fixed TCR SVC, a small inductance is connected in series with the capacitor and tuned for the selected harmonics, and apart from that there should be a harmonic suppression filter. It is also a high pass filter used for the mitigations of the harmonic. Now, the purpose of the mechanically switched capacitor is to generate a stepped reactive power. Once it will show in the next slide when it is been switched on. So, reactive power capability will change, because you are actually increasing the increasing the admittance of the line, thus more current will flow and the more MVR you will inject. TCR perform as a control reactive power absorptions, because it will go to the highest numerical number, highest unit of number. If it is every mechanical switch may have a capacity of 2 MVR. So, it will go to 7, and we require to let us say compensate at 13.6. That 0.4 volt will come from the TCR. Power of this, what it says, that power absorption when there is a excess var generation. In MSC TCR SVC, the rating, if TCR is almost equal to the singly mechanical switch rating of the capacitor. As per the requirement of the reactive power generation, the number of switched is on. For less reactive power generation, less number of switch should be on. Definitely, if it is 10.4, then you will actually switch on something, but you have to rather switch on another 12, because 6 and 1.6 MVA will has to be compensated by the TCR. So, what are the advantage? Advantage is definitely there is no complexity in it, and you will switch it on when it will totally discharged and switch it off when it is at the zero crossing. So, there should not be any problem, and it should be actually we have a bidder resistance to actually dissipate the energy stored into the system. That we will see in the last class in a practical coordination control of the fax devices in a one case study. So, advantage is the low loss and the low cost, and disadvantage are definitely more because it is using put in practice before the fax devices. So, slow response due to the mechanical switching, the switching closes around 2 cycles. So, for this reason we require to inject or insert this this actually reactance very slowly, and thus leads to the subharmonic oscillation, and open in 8 cycle. So, that is we have to check that we require to gradually dissipate the power and open it. So, it is not used for the large dynamic reactive power variation, and it is for the also for the fast dynamic reactive power variation. If Var demand would repeatedly change above and below this level at which the capacitor bank is switched in and out, then the MSC TCR SVC cannot be used, because switching life is limited to 2000 to 5000 cycles. So, we have to operate this actually operation very constrained manner, so that we can use it for the longer duration. And another issue is that the trapped energy in the capacitor bank which result in transients. So, capacitor always been a little nasty when actually transient phenomena occurs. Therefore, each capacitor has to be completely discharged through a bidder resistor, which makes around 8 cycles. You have to dissipate all the energies. Before being switched, we use potential transformer PT also sometime, but generally it will also increase the cost of doing it. Thus, we can conclude that because of much slower response and the limitations of the limitation in execution of the capacitor switching, the output of this MSC TCR combination would not be able to allow to exchange the reactive current reference. So, we had to be fitted with the dynamically controlled TCR. It can be used in rate of change, it can be used where rate of change is very slow, or a single step like change must be taken place in time is already discharged, and we can go for the next switching stage. The thyristor switch capacitor is another combinations. So, instead of the fixed capacitor, we may have actually mechanical switch capacitor. You may put it on and off by mechanical switches. Now, you may have a TCSC TCR is a combination. So, then you will also have a thyristor switch. So, it can manipulate turn on and turn off, as well as you have TCR. So, thyristor switch capacitor and thyristor control reactor TCR are the type of combinations. Actually, compensator was developed for the dynamic response with minimized standby losses providing the increased operating reliability, because you can also frequently turn on and turn off this TCR that is already there, and apart from that you have TCSC. So, that also can be turned on very frequently. As a basic single phase TCSC TCR typically consists of n branches of the TCSC, let us say have a rating of the 2 MVA. Again same example, you require 30 dynamically, you have compute that you have a 13.6 MVA. So, what you will do, you will actually switch on the 7 such TCSC, and minus 0.4 var will be actually provided by the TCR. That is the principle of operation of these combinations, it is very simple. Thus, the n number of branches n is determined by the practical consideration that include the operating voltage level, maximum var output, current rating, and the thyristor valve, etc. The inductive range also can be expanded to any maximum rating by employing additional TCR SCR segments of the branches. So, you can add on, that is all. So, you know, actually this is the one TCSC, another TCSC, and this is another TCSC. So, accordingly it will actually increase the Var compensation, and whatever the negative portion it will come. So, it will be actually making, let us say there are 7 such thing. So, that will be a 14 MVA capacitive, and we would require actually 13.6 MVA. So, minus 4 MVA, 0.4 MVA will come from this TCR. The total capacitive output range divided into an individual. The first interval, the output of the Var compensator and the Var generator is controlled to 0 to QC max by n. So, n is the actually the quantization, where QC max is the total rating provided by the all the TCSC branches. In this interval, one capacitor bank is switched on, simultaneously the current in the TCR is set to be set by the appropriate firing angle delay. So that the sum of the Var output of the TCSC and that of the TCS of the capacitive output is required. So, it will compensate the negative bar. The second, third and nth interval of the output controlled, that is, let us say this is actually QC by n. So, there will be 2 QC max by n and so on till QC max. So, you can have a step change in operation of compensating Var. We shall see in a waveform soon. In all interval, surplus of the reactive power is absorbed by TCR. That is what I was saying. So, theoretically TCR should have a same Var rating as TCSC, but we generally provide a little bit more. But switching condition at the end point of the intervals are not intermediate. So, Var rating of the TCR has to be somewhat larger, even though you can say that since the Q max by n you have chosen to be 2 MVA. That is a rating of the single TCSC branches. But here, you know, that is what it is saying, it has to be somewhat larger in practice that of the TCSC in order to provide enough overlap, because you know you require to have a hysteresis band, otherwise you will unnecessarily switching these devices. So, for this reason overlap or the hysteresis band between switched in and switched out Var level. So, you will decide. So, that is actually what is actually the window of hysteresis, whether it is 0.1 MVR or 0.2 MVR, that is something we require to decide, and based on that we have to provide this. The capacitor output Var QC is changed in a step like the manner of the TCSC, which we have discussed earlier. So, this is the waveform we require to explain. This is the Q demand and this is the L demand. Once you actually switch on this capacitor, so you get this much of Var. Once you get this much of capacitor, so you get a steps like compensations. Switch it on, you get. So, you can convert into the RAM, ultimately you will have this kind of RAM. So, that will be to operate it, but you can operate only this point, this point, this point, something like that. And accordingly that extra demand has to be compensated by the inductive Var. So, you can inject a little bit of inductive Var. So, you know actually you will have, this is the dotted line. So, once you like to go it back. So, once you come back, you come it like that, and you know this is actually the ramp on in that way. This is for one TCR, this is for another TCR, this is for another TCR. Accordingly, you can change the Var. Ultimately, you can make it also inductive Var demand by switching only the TCR. Thus, what we can conclude from these discussions, the approximate Var demand with a net capacitive Var surplus and a relatively small inductive Var output of the TCR and QL is used to cancel the surplus reactive Var. So, this is the actually small amount of the reactive Var. The rating of the reactor is kept relatively small, that is 1 by n times of the maximum rating of the capacitor voltage and the capacitive MVR. The control scheme for TCSC TCR type generator, and we will see that how it can be controlled. First of all, we require to know that what can be the maximum Var requirement of that particular site, and we came across, let us say we require, let us say 20 MVA, and from there we have to design the size of the modulity. So, what should be the one branch's capacity of compensation. So, let us say we decide of the all the constant thyristor ratings, transients, all those consideration has to be put into the operation, and if we find out that actually the 2 MVA will be the suitable. So, thus it can compensate maximum capacitive Var of up to 20 MVA by switching 10 such TCSC, and you should have one TCR of rating of around 2.5. So, that there will be a little overlapping and you can able to compensate in the right manner, and you can manage with the actually the combination of TCR and TCSC very well. The precision will be set by TCR. That first, so thus what happens, that determines the number of the TCSC branches needed to be switched in to the approximate required capacitive output current, and compute the amplitude of the inductive current needed to cancel the reactive surplus Var. First of all, you will compute, let us say 13.6. From 13.6 you will actually come down the number n, that will be 7 here. So, you are compensating 14 MVA, but exactly you require basically then TCR has to inject 0.4 MVA, and thus you compute the delay angle for it. Delay angle can be computed online by the processors, or you may have EEPROM, so that you have for every degree of alpha for a particular voltage rating. So, you know this actually what should be the value of alpha, that you can put it into the EEPROM with some precisions of 180 degree or with 0 to 180 degree with the precisions of 1 degree or 2 degree. So, you have to see that what will be the change in current for the 1 degree and 2 degree within a prescribed limit, we should choose the precision in that way. We shall come this a little later. Next slide. The controls the switching of the TCSC branches in a transient free manner. That is very important, since you are inserting capacitor. So, you have to do the 0 voltage switching that we have discussed previously. You know, we require to insert a capacitor. When you are inserting a capacitor, ensure that voltage, supply voltage and the capacitor voltage is same, or when supply voltage is 0, you are going to switch on this capacitor. Varies the current in the TCR by firing angle delay control. So, this is something the scheme of TCSC TCR SVC. So, you have n such TCSCs and you require the IQ ref. So, thus you can find it out what will be the number of such element, actually 1, 2, 3 to 7 is required. So, for this reason you will turn it on those. So, 1 to n. Thereafter, you know, you will have this is on off control, and there is see that actually you will sense the voltage of the TCSC, that is very important, of this capacitor, and accordingly you will give a pulse, and this scheme we will discuss little later, and you will give a triggering pulse of the thyristor to the TCR. So, First of all, first steps will be to determine the number of TCSC branches needed to be switched from this actually IQ ref. The input current reference IQ ref is presenting the magnitude request of the output current. So, we have to find the ratio of the current reference and current IC. So, then that gives you the number of n. Then n comes out to be 13 actually 5.6. Then you actually turn on 6 such things, and that actually the fraction part will be compensated by the TCR, and that TCR branch will draw at the given amplitude V of the AC voltage. The result rounded to the next higher integer, and this number of capacitor banks is switched. Then compute the amplitude of the inductive current needed to cancel the surplus reactive current. You find it out actually ICN. From ICN actually you will actually compute the current required, that will be IQ ref, and thus from subtraction you get basically that the inductive current to the TCR, that is ILF alpha. So, you require to compute the alpha from ILF. So, what we can say, the switching of the TCSC branches follow the two simple rule. One, we require to have a transient free operation, and it is either switch the capacitor bank when voltage across the thyristor valve becomes 0, or when the thyristor valve is a voltage when it is minimum. So, either of the circumstances you can trigger on to ensure that minimum transient into the system. The first condition can be met if the capacitor residual voltage is less than the peak voltage, and the latter condition is satisfied those peaks of the AC voltage who has the same polarity of the residual voltage of the capacitor. For this reason, you will sense this actually every moment, the voltage across thyristor, and also check the polarity of it, and then you actually design the triggering pulse in that manner. We shall come and see that actually triggering scheme for the TCR in next slide. For the third function, TCR firing delay angle is identical to use for the fixed capacitor, there is no change, and thyristor control reactor scheme. So, this is the actually the control logic. You have to sense this voltage. First of all, it will sense the pole voltage, that is called pole voltage, and also we have to sense the voltage across the switch. So, we want to have a minimum stress across the switch. So, what happens? So, if you have a on request, then first of all you require to synchronization with the actually PT. So, that is comes from the potential transformer, essentially is a voltage template, and it will and then it will actually also check the pole voltage, and then it will again what happen, you have on request, then you will check the switch voltage both. So, then it will AND it, and that OR it, you will give a triggering pulse, because there are two conditions. So, clause 1 and clause 2. When SW1 is high or 1 whatever, voltage across the thyristor is 0. That is something that information should carry. The pole voltage signal is 1 when polarity Vc and the polarity of the phase line voltage of the grid voltage are same, and PT is actually synchronized 1 when the source voltage reaches at its peak. So, TCSC is on when the request 1 and SW is 1, that means switch across this thyristor is 0, or when TCSC on when the request 1, this pole actually potential is 1 and the PT is 1, in the circumstances also it will put the thyristor on. So, thus what happen, this is the actually the admittance curve. What happen for this is actually you require to keep the rating of the TCSC little below than the TCR because of the voltage swelling of the capacitor. So, for this maximum VC max you can go little lower than the VL max. So, this is actually compensation. You can choose any compensation level for the VL depending on this actually amount of the current you are passing through, and that will depend on the voltage rating of the supply. And here if you wish to change it, then you have to, this is for actually TCSC1 and this is for the TCSC2, this is for the TCSC3, this is for the TCSCN. In that way this will go on. So, this is basically the VL max is the voltage limit for the TCR, C max is the voltage limit for the capacitor, and IL max is the current limit of the thyristor, and IC max is the current limit to the capacitor, and BL max is the admittance of the TCR, you can choose any value, and BC is the admittance of the capacitor, and it will change in this way. So, loss versus this characteristics, since it is device is turned on, if you are increasing alpha, so losses will increase. And actually what happened, initially loss will be high because it will have a transients, and thus the transient will settle down in that way. So, gradually high current will flow and it will come down. So, ultimately loss will stabilize in case of the TCSC, and while changing the value of the current you will have basically that will increase. So, what we can conclude, at or slightly below the 0 VAR output, all capacitor banks is switched out, the TCR current is also 0 or negligibly small, and consequently the losses are almost 0 or negligible, only the stray losses will be there. As the capacitor output increases, increasing the number of TCSC branches are switched on, with the TCR absorbing the surplus capacitive power. So, this kind of graph is prevailing. So, more you are increasing the current, so more we will have this kind of losses. Each switched TSC bank losses increases by a fixed amount with the transient phenomena, and same way for the TCR, as alpha increases, since you know that actually drop across the thyristor is constant, into current will give you the drop. So, it is, if it is giving you 1 volt drop across the thyristor, multiply the 1000 ampere of current. So, you get simply the actually 1 kilowatt of losses across each of the thyristors. So, come to the advantage of the TCSC TCS type SBC. Of course, you have a fully controlled, unlike the fixed and the mechanical control. The reduction of the reactor size, because you can play around little bit with the modular type TCSC, will consequently the harmonic is also generated, we require to suppress the harmonic. It got greater flexibility of control, precision can be set by the TCR, better performance under fault condition, because you have a switched one and you can switch it off or switched in the impedance part of the it to tamp out the oscillation. Power losses in the operating conditions, that is with SBC output current close to 0 tend to be less with the TCR TCSC type SBC than the normal one. So, this is the actually the combinations, this is actually compensations. You know, this value basically inductive value will be little bit more, and you have a maximum value of the current can pass through the thyristors for the TCR. This portion is actually the TCR compensation, and this portion AD is that portion basically that capacitic combinations. So, the characteristics ADB is the control range, you can actually have this kind of control range. Less current you can go to the little higher voltage instead of the capacitive, but capacitive voltage when you are fully, you have to little bit drooping the voltage compensation. The BC represents the SBC at its inductor limit. The SBC current considered the positive when SBC susceptance is inductive. SBC injected the current, it is SBC equal to minus BSBC into VSBC. The slope of OA is BC, susceptance of the capacitor, and the slope of OBC is BL, that is susceptance of the reactance. And what happened then, the steady state value of the SVC bus voltage is determined from the intersections of the system characteristics and the control characteristics. So, this is basically the system characteristic, this is the voltage, and you will cut to this one point. And generally when power factor increases, I mean that is gets better, the power increases and in a capacitive region, but you have a just reverse characteristics. Compensation characteristics will be this, and system characteristics, that is the voltage characteristic, will be this, and you will find the operating point, that point you will operate. The system characteristic is a straight line with a negative slopes defined by SVC equal to VTH minus Thevenin equivalent into SVC, where VTH and the XTH are the Thevenin voltage and reactance viewed from the SVC, where the point SVC is connected. So, from there actually we can go to the calculation, since it is a midpoint controller, we can find it out actually, that will V cos theta by delta by 2, and so from there this is actually the X TH, and where surge impedance will be given by under root of LC. So, we can have a control range. So, you have a SVC plus Vref plus this extra control current, where X is the slope of the control characteristics and Vref is the SVC voltage and ISVC at the 0 current. So, after solving, you can get, that is actually the voltage of the SVC at the midpoint of the sag compensator will be this value, and ultimately what you get actually Vm, that is midpoint, into sin delta by 2 Zn sin theta by 2. So, by calculating it, you can calculate the power flow, and the power flow will be V square sin delta by 2 Zn 1 minus x Zn into cos theta. So, you can see that you can compare with that V square by n by V square sin theta by x. So, you can see that you can reduce this, the denominator, by playing out this VTH into A. So, this multiplication can be 0.5, thus you can have a actually power flow control increase to the 2 times. So, this is our discussions of this actually TCR type SVC. So, we shall continue to discuss shunt time reactance in our next classes. Thank you for your attentions. Thank you very much.